Well, welcome. Thank you all for joining us today. My name is Mike Smith. I want to talk to you about how it is that we can get every student that is interested in learning how to computer program to actually be successful at that learning. Now, just to give you a little bit of background on myself, I've been teaching introductory CS classes at Harvard undergraduate since 1992. But it was really a recent experience that I had that I'll describe in a bit more detail in a moment that really opened my eyes to the fact that we needed to do more to reach those students who I claim weren't naturally enthusiastic about learning to code. Um, Now, computation continues to become more and more important in a vast range of disciplines. And so I believe this group of students who need to learn how to code, but aren't necessarily intrinsically motivated to learn to code, we need to be thinking about how best to reach them, to teach them. So I sat down one day, took a critical look at what I and others were teaching. And what I really found was that today's, at least college level introduction to computer science classes, which is what I know well, haven't really changed in the 4 decades since I actually learned how to do this. Now, of course, there's new languages, new techniques out there, but the approach that we use in today's classes is basically the same approach that we used when I first started out, which, given how much the world has changed and our students have changed, felt just like something crazy. So let's see if I can move to my next slide here. So I want to start and have a little bit of interactivity here. So if you wouldn't mind throwing into the chat answers to these 3 questions, and please go ahead and answer all 3 questions, even if you don't answer the first question affirmatively, even if you don't teach an intro to computer science class, still take from the classes that you've seen or things that you've seen online, like what topic does that class begin with? What does it cover first? Here, what I'm asking in the second question are things like, do you start talking about bits and hardware organization? Or do you first define what an algorithm is and talk to your students about that? Or do you start with a history of computing and talk about how fast technology has changed? Anything in that space. I'm just curious, after having done my own research in this space, what you and your school have done. And then finally, answer for me also, what piece of code do you show to your students first? Straightforward. So go ahead and throw that into the chat, and I'll give you a moment to do that. Thank you, David. Okay, so we have a lot of people starting out with binary, guess the number, and hello world. Some turtle graphics, some problem solving in algorithms, hello and Scratch. A lot of people starting out with hello, some logic puzzles. Excellent, terrific. Keep throwing those in, and I'm going to move on here. So what did I do? When I sat down and answered these questions, I came up with some answers I'll show you in a second, but I want you to now also pause and reflect on the answers that you gave and try to say, well, why is it that I do what I do when I start talking to the students for the first time in the class? And why do I show them this first piece of code? All right, so do a little bit of just self-reflection in that space. And let me tell you what I did when I started thinking about this. My 2 answers for what topic do we start with, it's because that's how I was taught. And also because I thought the particular things that I started teaching were the ones that interested me in the subject and therefore might interest the students. Now, I probably don't have to tell this audience, these aren't great answers to these questions, right? Especially the second question, the second answer here, or what interests me. I've learned very much that today's students are not interested in the subject in the same way that I was at their age. And that's hardly surprising. The world in which I started a program looked like this. I started on what's called a teletype, which is what's in this picture here, connected to a mainframe, which none of my students understand when I use that term anymore, that was connected to a mainframe computer at RCA Labs, right? I took home my programs on paper tape, which is the line that this thing that's coming out of the left-hand side of the teletype is the paper tape. And the ones and zeros that we talk about in these classes were very real to me at that time because they were the holes and not holes in the paper tape. Now, of course, you may say, sure, you're old as dirt, which is true, I am. And technology moves very, very fast. So, maybe today's students are going to be interested in the same thing that you're interested. But I believe you don't pay attention to how fast technology is moving. Today's students are thinking about using technology in ways that weren't what we were thinking about doing. No matter how old you are, your students are growing up in a different technology world. I actually did this a couple of years in my classes. I asked my students if their younger siblings were growing up with the same technology and approaching it in the same way that they did. And every time I got the answer back that no, their younger sibling had a very different experience with technology. So this rate of technology change matters tremendously in this space. So second question, or third question in the list, why do you show the particular piece of code that you show first? I saw quite a few people write down hello world. We're lucky enough to have David Malin with us here today. He talked about running with hello world. Even Replit itself, if you create a REPL in C, the first thing you get is example code that is the syntax, the code for hello world. And it's nice. You can write this program in any programming language, and that ubiquity is quite nice. But I sat back and I said, what are we really emphasizing when we start with this code? And please go ahead and add it to the chat too. What do you think we're emphasizing to the students when we're starting with code that looks like this? If you saw David's talk yesterday, you did see that he gave some great reasons for why he was doing it. So we're seeing quick output, some syntax is coming out, a little bit about input output, another syntax, getting the computer to do something. Excellent, terrific. So I agree with this too. When I asked myself this question, the first answer I really came up with was syntax. And so I did a little investigation. I said, am I the only one thinking about this? And if you go read the Wikipedia page on Hello World, which there is one, the second sentence on that page says, this program, and I'm quoting, this program is used to illustrate a language's basic syntax. Yeah, but you might argue, look, we're following what the giants Brian Kernighan and Dennis Ritchie did in their 1978 book, The C Programming Language. And in fact, their preface in that book says this, and this is again a quote, this book is meant to help the reader learn how to program in C. Now, English, of course, is ambiguous. Does this sentence mean learn how to program, the emphasis being on the yellow words here, and we just happen to be using the C programming language as our active learning environment? Or is the emphasis on the back half of this sentence, learn how to program in C, right? In other words, you know how to program already. Now let's learn how to do that in this particular language, the language of C. Unfortunately, the interpretation, as the next paragraph in their preface says, and again, I will quote, this book is not an introductory programming manual. It assumes some familiarity with basic programming concepts like variables, assignment statements, loops, and functions. Brian and Dennis started with a program that they thought would help someone that knew how to program to get started in this new language. So I sat down, I said, is this really what I want students to think programming is, especially those students who are not intrinsically motivated to learn this material? They just know they need to know it. They need a competency in it. Now, I will absolutely agree that syntax is hard, right? Computers are literal. Compilers and interpreters can't deal with the ambiguity that we just discussed. But is that really where we want to start with the students that want to be motivated to learn this? And so I went back to thinking about with my children, what did I teach my young children when they were starting to talk, right? I didn't explain them the syntax of our native language. What I simply did was encourage them to express themselves by turning ideas into words. Now, I gave them feedback when I didn't understand what they were trying to say. And then I only slowly taught them proper syntax when it was necessary in order for them to be actually clearly understood. But I didn't start with the syntax. So I want to now, with that context, tell you a little bit about a new course that's called CS32 at Harvard and how I came to teach it. CS32 is in our curriculum as an alternative to CS50, the very popular introductory computer science class that David Malin teaches. Our students can take either CS32 or they can take CS50 because both have the exact same learning outcomes. They won't end the class with any different learning outcomes. And I want to emphasize here that CS32 is not a replacement for CS50. It's just an alternative approach to teaching the material. And what do I mean by this? I'd say at its core, CS50 is following the approach that we've been discussing here, that syntax matters, CS concepts matter. Let's talk about those first. And this works for a great many students. We've got terrific people coming out of David's class. And David has done an amazing job in teaching CS50 since he took it over in 2007. Now, in full disclosure, just since I'm pumping up David here, I was his teacher, I was his PhD advisor, so I'm admittedly biased, but it's a great course. And when I taught CS50 before David, I fully bought into this traditional approach. But my career path took me away from teaching for about a decade, as you can see here on this slide. And when I came back to teaching, I was rusty. And so when I went and taught the next class that I taught, which happened to follow on from CS50, I was really attuned to listening to the students' experience in my classroom. And what did I hear when I was actually really listening to them? What I heard was this question. I began to teach them a concept or a piece of syntax, and some students in the front row of the classroom would be looking perplexed, and I'd ask them why. And they go, well, why are you asking me to learn this particular concept or this particular piece of syntax? And when I dug a little bit deeper, I often found that the students that were asking this question often were the students that were not motivated because they loved the subject. Like, okay, tell me something else. Tell me something else. I'm just sopping up all of this information. They knew they needed this competency, and they knew they needed to be able to solve problems that they cared about. And what they wanted to know was, why are you teaching this? How is this going to help me in the future? So my goal in my new class in CS32 became to never have a student in my class ask this question, right? And the easiest way that I saw to accomplish this was to kind of flip this script that we've been talking about, right? So instead of what I call the traditional approach, look, you really need to know this concept. You really need to know this piece of syntax. So I'm going to tell you about it. And then we're going to give you some examples of how it's used. And then we'll give you some program that might be interesting that uses this concept and this syntax. I put it here. I don't know how well you can see it on your screen, but the table of contents for one of my favorite introduction to programming in Python textbooks that's by Robert Sedgwick and his two colleagues at Princeton. And as you can see by looking at this table of contents, the organizational form is clearly on concepts and pieces of syntax, right? Example, in section 1.3, we're going to learn how to express conditionals and loops in Python. Some students are excited about that. Others are like, okay, but why? Right? And then again, I really like this book because it eventually comes at the end to give a real life problem. And so what I asked myself is, for this new class, can we teach a novice, someone who has no programming experience at all, to program by flipping around these two steps? What if we put the interesting real life problem at the start of the chapter, and then the context becomes obvious why we need to learn this stuff. And then once we've done that, then as we're trying to solve that problem, we teach concepts and syntax that the students need. So that's what we're doing in this new class that I taught this last year. And since I've spent a lot of time telling you about the issues with the ways that we have been traditionally teaching for these particular class of students, let me tell you how exactly I have started my class. And I actually start before my class. I take the list of students who have enrolled in the class, and before they even show up in my first class, I send them a link to a video and I tell them, please watch this video. It's a short couple of minute video that answers the question, what is a computer and what is programming, to try to put them in the right frame of mind. No matter what they've heard before, I want them to be thinking, as it says here on this slide, computers are flexible tools and you use them to solve thorny problems. And you can do so with great and tremendous creativity by programming it to have them do what you ask them to do. And I compare in this video a tool that I claim is a fixed tool, a shovel. It's very good at what it does, but it only helps you dig holes. You can try and do other things with it, but it's not very good at that. And probably how they've been using computers to this point for a very particular task because they know it. And now they're going to be open up the world of, I can get this computer to do other things for me. So once they get to class, then I start with an emphasis on problem solving. Every class starts with a problem to be solved. They're in, hopefully, the right frame of mind here. And what I'm really doing is teaching them how to use computers and computational thinking to solve problems. Right? I don't start with any of the traditional openers. I don't tell them anything about the history of computing devices. I don't define algorithms. All of these sorts of things come later in the class when we've gotten to a point where it makes sense within the problem or the students are asking for more information. So if I'm not giving them foundational information to begin with, how am I actually getting them to start in the class? Well, I'm doing this. My instructions on day one when they walk into the class are 4 things. I put this on the board. Be curious, be creative, ask questions, try things, right? I want them to be active in the classroom. No sitting around passively taking notes. Now, if we want them engaged in trying things, of course, I need the students immediately into a programming environment. This used to be a huge hurdle in our programming classes, but isn't anymore, especially with these browser-based integrated development environment, IDEs like Replit, product placement. All right. So what we do in our first class, as soon as they walk in, I have all the students join our team, and then we jump directly into a Replit project. Bang, we're going. This is about what the students see, right? We have the right tools, but now the students are looking at a blank page. This is one of the scariest images to a new student. Nothing in front of them but a blinking cursor. I found that their mind starts racing. They begin to panic. They say to themselves, I can't write anything. I don't know Python. I don't belong in this class. I acknowledge the fear at this point. And I tell them writing in Python or any other language is a step in problem solving with computation, but it's a later step. We don't need to do it now. What we need to do now, you can do. And what you can do is start to define the problem to be solved, right? So I've given them a problem to be solved. The problem I actually give them here on the slide is to tell them that we want the computer to read a book to us. Now, for those of you who've been programming for a lot of years, it's basically CAT on a Unix system, right? Most of them don't know that. And what we have to do is talk about, well, what does this problem need to do? We're keeping them in the mode of, look, nobody knows how to do any of this stuff before we do. We're just going to put ideas to paper, start writing some things down, allows me to talk to them about pseudocode, allows me to talk to them about comments. And that's what we do. We start writing things down so that the computer can write us a book for us. This leads us to, as we start doing this, to the second problem. Good. My screens are not synced, but anyway, to the second problem. Once they realize what we're trying to do and they start writing it out, we realize second problem in solving any problem is to understand your inputs. For us, if we want to read a book, what book? What form is this book in? Well, the project that we cloned in Replit happens to have a book in it, at least the text portion of a book, none of the annotating pictures that come from this Dr. Seuss book, but that's okay. I explained to them, look, we do not have to start solving the most complex instance of the problem. When we start, we can solve a simpler one. And then I asked them, when you were a little child and the book was read to you, what was the first thing that the person reading the book did? So again, if people can help me out and write down into chat, I'm not reading the rest of the chat while you guys are talking. Hopefully, I'm sure there's great conversation, but throw into the chat now. What's the first thing that people did when they read a book to you or when you read a book to your children or grandchildren? Anthony, thank you. Open the book. Sometimes talk about the author. Excellent. Read the title. Right. Terrific. So lots of different answers to this. Eventually, someone in my class says, look, we need to open the book. So that's what we do. We write down a statement, just a comment that says, open a book. So notice we're using pseudocode here and comments to help the student perform the problem solving. I've had tremendous difficulty in the past dictating to them it's good practice to write pseudocode before you write Python code, right? Here, the students are just putting their ideas down on paper. They're not thinking about it as pseudocode. They're not thinking about it as comments around pieces of Python code. They're just trying to write down what it is that they might need to do as they go forward to solve this book. Now, I could have the students write out a lot more things, but I want to quickly get into actually being active and trying things and experimenting. And I want the students from day one to be comfortable with experimentation in our class, right? Because things will happen when they do them. And we can learn by observing what the computer does, the same way as we were children. When we would say something, we learned by how our parents reacted to the kinds of things that we said. And then we adjusted on that. So I quickly introduced commands, and Python's very nice for this because commands in Python look a lot like English commands. So we write down, open. The first thing we want to do is open the book. Open. What book do we want to open? We want to open Cat in the Hat. And we start running things. And I ask the students to think through what happens when we do different things. What are they observing in these experiments? What do you think the computer actually thought we meant, and so forth? When I talked to one of my biology colleagues at work one of the other days, he's like, oh, that's exactly what we do in biology. All we're trying to do to figure out how the human body works, for example, is we go in and we break things and then we see what happens. In many ways, we're doing the same thing here to help the students start to put together in their mind how this environment really works. And along the way, of course, I introduced tools like help and other things that help us to actually understand. I spend a lot of time saying, how is it that I, as an instructor, also figure out what happens when I don't completely understand what's going on, and something I think we need to do more in our introductory classes. But let me fast forward here so I can get to the end. So this is a little bit longer into that first class. We've gotten to the point where we're able to open the book, we're able to read 2 lines, but as you can see on the right-hand side of the slide here, we've got extra output blank lines, and the students are getting into the groove of asking questions, and they want to know why. And so now I'm answering their questions, the questions that they have, not things that I'm presenting to them and saying, you should know this. So we fixed this, we fixed the extra blank lines, and then I'll ask questions like, sure, we copied lines 4 and 5 and put them down as 7 and 8. To read the second line, do we want to do this for the 3rd line in the book and the 4th line in the book? Do we even want our program to be closely tied to the number of lines in this particular book? And of course, the students go, no. And so now we're motivating why it is that we need to put loops and conditional statements into our programs. And so we do that by writing, okay, well, what does a loop look like? And for those of you who know, if you look at my pseudocode here, we're basically producing an infinite while loop with a simple condition in it that's the exit condition. So we're teaching them little bit at a time. We don't learn all about all conditionals. We don't learn about all loops at one point. We just learn what we need to do to solve the program that we're actually, to solve the problem that we're actually doing here. So let me fast forward to the end of the first day. And this is the code that we produced by the end of the first day. If you take a look at this, you'll notice that what did we need to discuss? Well, we're not discussing, as I said, everything about, they only leave this first class knowing about infinite while loops, right? They don't know anything about for loops that they'll learn in a later class with a different problem. Nice thing is that they'll come to me later when they learn about for loops and they'll be, okay, I've seen we're using them in different places. Why? When do I want to use one? When do I? And again, it's their motivation to ask me as opposed to me saying, you can use a while loop, or you can use a for loop. And by the way, you can make both look like each other and so forth. We don't cover all kinds of if statements in this first class. We only check a single condition and we only act on that condition being true. We don't act on a condition not being true in a different way here. And they don't have any real concept of objects. They had to learn about object because they had to learn that some commands are returning an object that they need to name if they want to use it again in their script. So they're starting to get an idea of what's going on here. Importantly, though, they leave this first class having built a script that directs the computer to read a book of any length, which now to them sounds like a non-trivial exercise, having gone through what to do here. And I've really helped the students start to learn to problem solve, right? What, if you look at this, what I've basically given them is a work list algorithm. And so we'll spend the first couple weeks of class just doing work lists algorithms, problem solving, so that they're getting used to turning a work list kind of problem into something that they can write in code and they can write syntax for. All right. I've given you a little bit of a flavor. I don't have time to go into a lot more. There's a lot more to this. I'll be happy to chat with you about how this works. Let me just say here before I leave, one of the things that we also spend a lot of time with For example, how many of you find compilers and interpreters, the error messages that they spit out to be cryptic, it's very frustrating and intimidating? I can tell you I do. I can tell you my students certainly do. And it's one of the most frustrating things because they're looking at it and they're saying the computer, the compiler, the interpreter told me I did it wrong. I'm like, no, don't do it that way. That's not how you should be thinking about this. So from day one, we think about programmers and playwrights. And I want the students to be thinking about themselves as playwrights, directing an actor. The actor just happens to be a computer. And just like a playwright who writes something down and then tests their early drafts of their script with their theatrical troupe, and then gets immediate feedback from this troupe on the success of what they wrote. What did they have in mind, and what did the actors actually do? And what was the difference between that, and how can they adjust then their scripts to get to the point of what they really want? Or maybe they learned something from the actors in that troupe, and now they want to build it into the way they're doing. So getting them to stop thinking about the computer as telling them they're doing things right and wrong, but the computer giving them feedback is a big piece of what we try and do in this classroom. And then finally, hopefully that inspired in you a little bit of thinking. Again, I'm happy to chat with you if you have more interest in this kind of an approach. I've given you my email up there. We have a curriculum jam coming up as part of EdFest, and you might use some of that time to try and rewrite, as I've said here, one of your lessons into a problem to be solved. Here's some of the things that I would encourage you to think about as you try this, because I find it actually harder to do this than it sounds. Like, I just flipped my script. This shouldn't be too hard. Here's some things that I learned as I built the class this past year, one of which is always start with an interesting real world problem. There's lots of them out there. For example, one part of the class, I start with, how does Google search work? Huge problem, right? We don't try to talk about all of Google search, but the students understand how Google search works, at least at a high level, and we start to decompose it into core tasks, right? Again, I'm teaching them problem solving. Problem solving requires us to take a big thorny problem and decompose it into core tasks and then solve those individual tasks. I identify one of them that's computationally solvable and has a piece of syntax or a concept that I want to teach next that builds on something that they already know. Then we solve, as I said earlier, we don't have to read a book with all the pictures in it. We can just read the text. So find a simple instance of that important task and then go from there, right? A hard thing here is when you find yourself slipping into, you really need to know this concept. How are you going to motivate it first? Step back and motivate it. So anyway, that's it. Thank you for staying along, and I hope you got something out of it. And I'll go back and read all of your comments now.